Yes, students, good afternoon. Let us begin our class. You will have your exam 1 on Wednesday. And today I will discuss about your project and a new material which is dominant pro. Okay. We will discuss first about your project. I decided that both group in project B1 and project B2 you will create the same thing. Okay. Previously project B2 will create the model in MATLAB. Okay, but now all of you, I want you to create the real model. Okay, bicopter model. And then the step number 1 is for you to manufacture the bicopter, and this is due in mid-October. Okay, you have seen the bicopter model in the previous lecture, right? So I bring the parts here so that you can see. Okay, so this is the frame of the bicopter that you're going to make. Yeah, actually this is the frame I take from the drone that we have in IoT lab. Okay, so group 3, 4, and 6, you will create one model. Okay, and also group 1 to 5, you will create another model. So this class will have total 2 models. Yeah, and so these are the DC motor that you will use. Okay, we have more than enough DC motors to be used. So you will place your DC motor here, and then another one on the other side. Okay, so this is the DC motor, and then on top of the DC motor you will put your propeller. Okay, let me put it in so that you can see it clearly. Yeah, okay, it's not easy to put it on, but you will put your propeller in one of the is this the correct one? Yep, one of them will be here and the other motor is on the other side. Okay, you will have the motor and also the propeller on the other side, and on the middle you will install a ball bearing. Yeah, so it will have a pivot in the middle. Okay, so it's going to be look like this. You have your pivot here, that's the pivot, and this is your motor, and then you have your propeller here. Propeller over there. Yeah, that's the propeller. And then of course also inside the pivot you can have a big box over there, and the box is where you put your controller. Okay, you have the controller, you have the battery. Okay, and the purpose of creating this is that so that you can perform position control of this model. Let's say you want to have some desirable angle, theta d, let's say. So you program the system, then the bicopter should go to the desired angular position. What do you think? Do you think it is going to be simple, or is it going to be difficult?
The project kan has two project. One project has three group. The three group become one group.
Okay. So the three group, you create the model together. Okay. However, you create the controller for each of the group. So each of the group has different controller.
Same design.
The same thing, the same physical system. Okay.
The difference between the one and two.
Only the students are different.
Like the model should be how different.
The model will be different depending on your own design. Okay, that's, and then you will have the same ingredients. I will give you the same ingredients, same motor, same chassis, only different color. Okay, one is black theme, one is white theme. Okay, black and white. Yep. Or you want black and white together? No, the design is just like that. Okay. The most important thing is that you put the propeller here. Propeller here, it's already, you know, it's easy to assemble. You just put the screw. The 3D printing done is over here. You have to create the pivot on your own. So only the pivot is something that you have to create. Yeah. But then for the pivot, you can connect a 3D printed design to this four screw holes. So it has a screw holes which you can incorporate into the pivot.
And the ball bearing,
No, I will purchase it for you. Okay.
these groups,
Yeah, two different
We'll
chassis.
be sharing the component.
No, the component, you have the component for B1 and B2 components are available. So you are not sharing. Sharing means you are using one component for all of them, right? But for B1, you are sharing components. That's correct. For B1, let's say G3, 4, and 6, you are sharing the components, but then you have to design the controller on your own.
Like we will have the same we will have.
Yes.
So we just plan Arduino and override the coding.
Yeah. That's how we do it.
so for one class, there is only two bicopter.
Yeah, 2 bicopter. Okay. Next year we will have maybe 4 bicopter, additional 2. This year we will make 2 only.
So we don't have to make the simulation.
No simulation. Okay. I think this one is difficult enough for you to do. So let us see how difficult or how easy the project is. Okay. Hey, to design the controller, you need to know the physical model of the system, right? You need to know the plant model, the transfer function of the system. How do we obtain the transfer function of this system? Okay, let me explain one by one. We have this propeller, and then the pivot here. There is a spring, but spring in the original model given by the UA professor, but I disagree that we have a spring over there, so I remove the spring. And then P is the point of the pivot. I call it point P for our reference. And then the length from the propeller to the pivot is assumed to be L/2. However, in the equation of motion, I assume that the length different. Yeah, when you are manufacturing your pivot, the distance from your from your propeller to the pivot may not be the same, right? Left and right, they might not be the same. Do you agree with me?
My left and right may not the same.
It may not be the same because of manufacturing error.
Oh,
You see,
like
they on paper they are the same on paper, but in reality they are not the same. Okay. And the next thing I want to say is about F1 and F2. You can control them independently, okay? Because through the this is called the motor driver. Okay, the motor driver, you connect it to the motor like this, yeah. And then these two cable here is the power cable where you input 12 volt voltage source, and this is the signal cable which you will connect to the Arduino. Okay, this one. So that means you can control the rotational speed of each propeller independently from the Arduino pins, correct? Yeah. Why you have to control it independently? Say it again.
do we assume the thrust to be linear?
What do you mean?
Propeller thrust is not really dependent on the speed, but it's dependent on the speed, but it's
Ah.
not really linear.
That's one of the difficulty of the modeling. Okay, the thrust itself is not linear to the rotational speed. However, your moment here is caused by the thrust itself. Okay, so that's going to make some kind of non-linearity in the model later. Okay, but we will do the modeling on the propeller itself and also on the motor. Okay, we will see later. Another thing I want to say here is about the Q. Can you guess what is Q here? Yeah, center of gravity. Okay, center of gravity will not be guaranteed to be on the pivot itself, right? Correct? Can you guarantee it is on the pivot? I cannot lie. It will be a lie if you say it's on the pivot. I will not believe such thing. So this Q here represents the offset of your CG location, and it will create a moment. Okay, the moment. Yeah, which shows here. Yeah, the term cosine theta here is non-linear already. I haven't converted into Laplace transform yet. Yeah, this one is still in differential equation. We haven't go into the thrust relationship yet, and the model is already non-linear. Yeah, Laplace transform cannot handle non-linear model to the way, to the extent you learn lah. It cannot handle the non-linear model. Okay. Now the theta here is the orientation, okay, of the bicopter which you want to control. Okay, let us see the first equation over here. I haven't included the offset of the CG. We have the moment caused by the propeller thrust, okay, and then C times theta dot. Do you know what it is? Friction, correct. It's friction, not tangential speed, but friction. So the C here is friction coefficient, which we assume to be linear. Yes, coming from the bearing. What about this JP? Anyone know what's JP? Something related to mass. No. For linear motion, you have mass, but for rotational motion, what do you have? That's correct. Rotational inertia of the whole thing. Do we know that? Do you know that? No, you don't know. Okay. So how do you make the controller if you don't know? You don't know who's in row. Not funny, yeah. Uh, okay. So already in here, the C variable C is not known, right? JP also not known. JP consists of the mass and also the radius of what? Radius of gyration. Okay, move on to here. Another term comes in, yeah, the Q here. Q also we don't know. So what are we going to make then? We don't know everything. Okay. No, we are not going to assume.
We find everything when the shape of the equation. All the numbers.
Yeah, how to find all of those numbers? That's okay. Yeah, through experimentation, we hope you are going to find those parameters, but not in exact format like this. Okay. You can still imagine the situation now, or you're a bit lost? Who's getting lost now? Which part? We are trying to find out the parameters like the C and the Q, the JP. Okay. Yeah, because it is difficult to set what we want. Let's say you are creating a car, a small car, and then you have the 1 over ms square. This one, yeah. Let me write it here. So this is a linear motion problem. It has a mass, and then your transfer function is found to be 1 over ms squared. Right? So what's the mass of this car? Can you measure it? Yes, you can measure it. You have to nod. Yes, you can measure it. So what's the problem if you put this mass into the plant? What's the problem? Don't you think there is a problem? What type of instrument you use to measure the mass? Scales. Does it have error?
Yes.
So the mass you put here, is it the exact mass? No, so that's an error, right? You get what I mean? What I mean is that the number that you intend is not going to be realized. We don't know for sure whether the number you put there is really the correct thing. Okay, that's why you cannot put them exactly. Okay. Yeah, the same thing with this. Oh yeah, that's true. Now what you watch the Thomas and Friends? Is it the Ferdinand? Ferdinand says that's right. Is it?
Wrong one.
Okay, let's move on. We just now we discussed this part, yeah, this part, and then I want to convert the whole thing into Laplace domain, and I have a problem with the cos theta. Yeah. So I convert this cos theta to be a very small angle. I assume it is very small. So cos theta, I assume it to be 1. Not equal to theta, but equal to 1. You make it equal to theta if it is sine theta. Okay. So when I convert it into Laplace domain, I just have the 1 over s over there. Anyone have a problem with this? We assume theta is very small, so cos theta for a small theta is close to 1. And you convert 1 into Laplace domain, you will have what? 1 over s. This one. The rest of the term, I have f2 over s, f1 of s, okay? And these are the thrust coming from the propeller. Yeah. And this is the uppercase theta we have in here, uppercase theta in s. This is one s squared. And so we get to the last line of the equation. Can you guess that this is the denominator of the transfer function? Yeah, this one over here is the denominator of the transfer function. Yeah, as we can see here, that's the sorry. Because you multiply this term to the output that you want, right? And so this part, you move it to the right, it becomes the denominator. Okay. And this is the block diagram. So far the block diagram looks like this. So far. Yeah, because the relationship here, we still don't know. Okay. What do you think your control will be here? Physically, it's going to be what? The control here? The Arduino is the controller, right? So what is the signal you send to the motor? PWM, voltage or current? Does it change the voltage or the current of the voltage? Yeah. So you are actually sending a voltage out from the Arduino, okay? And the voltage is going to affect the rotational speed of the motor, and the rotational speed of the motor is going to affect the what? The thrust. Forget which way is it? I think it's this one. Oh, okay. Yep. Does anyone need a proof that the thrust is related to the rotational speed of the motor? You agree, you believe me, right? I don't have to prove it, right? Okay. Yep. Yeah, actually, I have to hold the base and then can rotate. So where were we just now? The offset of the weight here, we assume it as a disturbance. Okay, this is a disturbance coming to the system, and so the output from your controller is the moment, actually. Yeah, moment, and then you apply it to the bicopter. But to arrive at the moment, you have to go through several steps. You apply a voltage to the motor, and then the motor rotates. It gets thrust, and then you get your moment. As just what Haikal pointed out, the voltage that you send to the motor will not be linear. Okay, it's not going to be linear. Oh. Yeah, another thing that I read here is that L1 and L2, they are not the same. They may not be the same. Okay. So let's say the controller know how much moment you need to apply. what is the force you need to apply here and over here. Can you tell the controller that? Do you know what I mean? Let's say you need to apply, you have to apply 3 Newton meter, let's say 3 Newton meter, and then that's clockwise, and then you can apply the force independently here and here, but we don't know the length L1 and L2. We don't know that. How we should apply the force in here? Say it again.
We tell the pressure motor to apply force thrust, but it's not. Yet
There will be an error. Okay, there will be an error. Yeah. Yeah, I'll leave it to you lah on how to get the strategy. That's part of the project.
That's a below the problem.
To what?
So you can see the like also you said sorry tilting.
Oh no, you will install an encoder in here. Encoder so that you can measure theta. You can get the value of theta. You want to you want to control theta, right? You want to regulate this, so you have to be able to measure theta, right? Yeah. Yeah, not necessarily 0. Let's say you want to make it 45 degree. You want to make it 30 degree. It depends on the purpose. Like let's say you want to play with it, you want to make it jungkit, right? Yeah, you apply what sinusoid, or you want to make to hold the position while you put another weight over there. Let's say you put another weight, but you have to keep it in position. You can also do it. You put a weight there, hold the position. Yeah, that's the main purpose. To reach this desirable angular position based in face of all of the unknowns. Okay. You want to say something?
Why in that drawing when you don't know L1 can measure L1?
Yeah, the problem is that this will not be exact, just like this one. It will not be exact. What? You serious? If the error is small, then people will not have to study uncertainty, you know. Yeah. Let's say you put a mass there, can you still achieve the same? Yes. That's the same thing, same kind of thing. Yeah. We can put a mass there, or you can disturb temporarily to see whether your system is stable, or it can reject the disturbance. Okay. Yeah, there is a saying that I want to say here. You cannot control system. Sorry, you cannot control a variable that you cannot measure. Yeah, you want to control the angular position, you have to get that measurement. The measurement here, does it have an error? The measurement of this angular position using encoder have error, right? Yes. Also have an error. In the class, exam, homework, we assume there is no error and the math exact. But in this experiment, all of those uncertainty are there. Yeah. Okay, let's move on. I have the model here of the DC motor, okay, and then the propeller here. So this one is just showing relationship between the current I, this is I is current, yeah? And then the omega of the motor, rotational speed of the motor. Omega m is the rotational speed of the motor. Yeah, the B, Jm, Km are all constants, which we don't know. Hey, we don't know the constant. So if you want to apply control signal at the voltage level, do you get what I'm saying? Say, you want to give a control signal to the plant at a voltage level. Let's say you want to compute how much voltage you need. Then you have to compute also, not compute. You have to find this Jm, B, Km. Okay, this L, R, K, KB. See, the list of the parameters just on and on. You agree? Yeah. You think you can do it? Yeah. One day. So it cannot be just done in one day. So you have to do it from Wednesday. So Wednesday, when you don't have the XML experiment, you have to do that. Okay. So the XML experiment is replaced by this on your free time. Okay. So your data equation in here will be combined with this. Yeah. However, from the omega to the thrust, we don't know the model yet. Yeah. So if you want to be exact, you can find the thrust relationship with the omega of the motor. Will it be more complicated then if we add the thrust? Yeah. Because omega is not linear with the thrust. I think it will be interesting. Yep. So any idea of how we get the parameters? Huh? From me?
No. You're asking when parameters.
Yeah, how do you will get your parameters? You have to design the controller, right?
Actually,
Sorry? What then?
Yes, the data gives to the design data. And the other parameter like data and the omega.
No. Finding this JM, B, KM.
Omega N is zero now.
Omega M zero, he won't move. Won't move lah. Yeah. Say it again. What? Number 1 and 2. Okay, number 1 is simply mass times acceleration. Okay, this is mass. Okay. Angular. Okay, and then this is the torque. Okay, it's a torque. The omega is speed, right? So you take the derivative of the speed, you get acceleration. Okay. Mass acceleration is equal to the torque applied. Yeah. And then this one is just coming from the Kirchhoff's law. Yeah. At the current. So the total voltage in here is just R times I, and then this is the inductance
Oh,
Okay, and this is from the eddy current. Okay,
Like, what is the equation? What
you have to find out these parameters. So these two equation is going to give you relationship between the rotational speed of the motor and the voltage you apply to the motor. You get what I mean?
omega is
This one omega here rotational speed of the motor. Yeah,
so ideally
this one rotational speed of the motor. This one.
so ideally you have two certain functions.
Two transfer function? No. You can view as two, which is from the voltage to the omega, but then from the omega to the thrust, you can relate them also. Okay, so the input coming to the system is the voltage, and then the signal you give into the system is the thrust.
Because from
So
now,
it's kind of
one function is from the angle, right? That is the function of
yeah.
the third.
Yes. You can connect them because F1 here, F1 is due to the omega over here. Yeah, F1 is a function of the omega. So you replace this F1 by this whole thing multiplied by the voltage, and then you multiply by a constant which will convert the rotational speed to the thrust. Yeah.
So now we're trying to find parameters.
Yes. Thrust and omega. Yeah. If you want to control at the voltage level, yeah.
that's what we meant. What we
Yeah. Because your input signal from the Arduino is the voltage, right?
So if you talk about resistance and trust, we will get the same.
We hope so lah. We hope so. Because there is no motor that is being manufactured identically, right? I don't think they are manufactured identically. Even this propeller also has chip in here and there because of the accident, let's say. I'm smiling because I'm imagining how difficult it's going to be for you to do it. Okay. Anything else? Yeah.
So the propeller and thrust using some theoretical knowledge about the thrust.
You can, yeah. Which is why you can convert the omega into the thrust using a model, okay? And hoping that the model is correct or working. Yeah. Okay. Yeah, actually, in the experiment, you are not going to find out all of these parameters. So you will not doing that. So I bring you up to this point because I wanted to imagine, yeah, modeling with the first principle is going to take a lot of effort. This is called first principle modeling, where we have all of the parameters in their format like this. What you will do later is to perform model identification using black box approach. You still remember what Prof. Pulung said, the black box approach? So this is your bicopter model. You give a certain input and you record the output, and then based on this input-output relationship, you can create your model. So we don't need to know all of this,
If this is numerically, that's
not numerically, experimentally. Yeah. What do you think? Is it going to be easier? Yeah, easy, right? Because we don't have to think about all of those small things. The input coming to your system is the voltage, right? And then the output coming from your system is what? Theta. Theta is your output. So you get direct relationship from here to here. Yeah. You can read frequency response function just to get your knowledge up first. Frequency response function. This is one of the way to obtain the transfer function of the system. You will get transfer function from here. And then we are also going to apply ARX approach. Auto-regressive moving average. This is a discrete time approach. Yeah, but now your step, the first step, focus on the first step, create the model first. Yeah, which is due on mid-October. You create your model first. Yeah, the physical model first. After that, we move to here. Yeah, we will explore them together. Okay. No, not on this one. Just design the thing. Yeah, any questions so far? These two, we are going to learn them together. Okay, you are not going to learn them on your own. I will guide you on that. As long as you create the model correctly, then we can do it.
So for the project, we have to choose one or
No. We will do it together. Okay. So for this, we will apply the model. I think some of you can choose using this or using that. Yeah, and then you will still get the same grade. I mean, there will be no difference. The advantage is that some of you explore using FRF, some of you explore using RX, so that we can combine the knowledge later. Okay, so we are going to split the task. Yeah. Now I want to talk about speed control of a car. Yeah, speed control of a car. Are we done with this? We done, yeah. So we still have about 30 minutes. Yeah, just now I said that and this is the velocity, that's the traction. Still remember this? Yeah, this is the first order system model of the car. Okay, and then sorry. Okay, if let's say we apply proportional and integral control in here. So the format will be, so the Ks is going to be Kp plus K over S, and that's the velocity. Can you get me the transfer function from Vd to V? Yeah, can you do it now? No, on paper first, on paper.
Yes.
Yeah, can you do it on paper and then you let me? What's the result?
Itu kan dikali 7 itu. Itu kan over 1 sampai sama lagi nanti S dikali 1 tambah M kali tambah 1 function of oh iya dia kayak S ya.
So the closed loop, I will write here. The closed loop will be ya berapa ya? What's wait, KPS plus KI. Okay. Huh? Plus
S
KI. Yeah, so this is the GCL of S. Yeah. So if that's the closed loop transfer function, what will be the final value of the velocity if let's say the Vd is 1 over S? What will be the what's the final value? Huh? 1. Ki over Ki. Okay. So when we have the Ki over Ki, yeah, this is equal to just Ki over Ki, yeah, which is 1, and that means your V will approach the Vd, yeah. If you give Vd 10 over S, 10, yeah, so it will follow, right? Do we have any vector of M and C here? Is it related to M and C? So do we need to know M and C here? So that's the magic. Do you realize it now? Okay, even if your mass is not exact, you can still get final value to be 1. However, the real mass and your chosen controller is going to affect the transient response. Okay. Yeah, that's correct. So that one, when you are going to work as a control system engineer, you have to do what? Fine-tuning to get the desirable response, transient response. But this final value is guaranteed. Yeah, you have to try. No, I mean the auto tuning in there is if we assume your M is something that you know, okay. But when you apply your controller later in the real system, you still have to try it because the M you put here and the M in the real car may not be the same. Yeah, and then the mass of the car is also going to change, right? one passenger versus 3 passengers versus only driver, different, right? Yeah, so with the same controller you have to make that the transient response between those different conditions are to be acceptable. They have to be at acceptable rate. Yeah. Even though the steady state error is guaranteed to be 0, you still have to guarantee that the transient response is at acceptable rate for all of those. Okay, any question on this? Yeah, and based on this, yeah, you can play with the model, and let's say you assume you don't know the exact value of those km, kb, km, jm, and jp. We don't know this exact value. If you use a certain controller like PID controller, can you check the final value of the theta? You can, right? It's just the skill issue of finding the closed loop transfer function, right? Once you obtain the final value, the closed loop transfer function, you can evaluate the final value theorem. Okay, whether the final value is affected by all of these parameters or not. Okay. Yeah. So the second step of the this one, the first principle, we did it almost done actually, but without all of the parameters. Yeah. In fact, I don't need you to find out all of the parameters, but I wanted to try out using this first principle modeling. Use your own hand calculation. Yeah, can you get 0 error? Yeah, that one. You don't have to find out this parameter, right? Using the analytical approach, you only need to try out whether using the PID, yeah, can you get the 0 error at the end without knowing all of these parameters. Okay, you try that. You can do it immediately. I wanted to discuss about the control of door, but that's the same thing I want to say. Same kind of. Okay, so I will move on to a different topic now. Is that fine? Okay. So officially, Wednesday you are going to work on the bicopter, yeah? Wednesday. No, on your SML time. Nah, I actually I will let it to do it when you want to see it fit. Sunday, Saturday you can do it. Yeah, making of the thing. Huh? You can bring it home. Yeah, it has to be done within 3 weeks, I think. Mid-October, 3 weeks from now. Okay, the next topic is this one. Dominant poles. Do you know what's dominant poles? poles that is dominant. Right?
Right.
That's right. Now, what does dominant mean then?
The most effective.
Not recessive.
Sorry?
Not recessive.
If you see a two-person, yeah, two-person working together or walking together or eating together in some kind of place, one of them could be dominant, dominating the other one. Huh? No. So what do you think dominant here then? Yes, the leading. So the dominant pole is going to affect the transient response of the system. We will see here. Yeah, we will see. Let's say you have a system like this. Which one do you think the dominant pole is?
This was 100.
Okay, we have two poles here, -2 and -100. Who said the dominant one is -2? Who said -2?
So,
Small one, yeah. It's very small, right? Who said 100? This one big, right? Big should be dominant, right? That's wrong. Yeah, the one that's dominating is the small one, closer to zero, just like Chris said.
yes,
No, I don't see the minus sign. Yeah, the closer it is to zero, the more dominating the pole is. So how do we see it? We apply, let's say we apply step input, okay, 1/s to the system. Step input. So what do you think we will get? Yeah. Can you compute it? CS. No, I don't want you to find out the final value, but I want you to find out what? No, this is GS. So this is 1/s times.
yes.
Okay, this is 1/s.
Yes.
100. And so this is equal to what?
That's great for
Oh.
S equals 2. Let's say we obtain the A, B, and the C. Let's say, yeah. So your CT will be, what's your CT? A times.
Yes,
Okay, this is just A, yeah. Okay, and then plus B times B/2, like this, and then plus C/100. Okay. How do we plot this? So if we plot this, yeah, we start with A, yeah. The value is A, like this. Not A, sorry, not A, but this is A plus, and then the end value is A, yeah. This one will go to 0, right? This one also go to 0. So your final value is there. I think this should be minus later. Later this one could be minus, and so if it is like this, then it just go like that, yeah. So this one, compare with this, it will go to 0 faster. Okay, it will go faster to 0. So you can draw, goes like that, very fast, go to 0. However, this one is a bit slower. Yeah, slower, go to 0. This one. So the one that you will see the most in the response is this one. Yeah, because the smaller poles, the further away from the 0, that one dies out very quick. This one dies out very quick, and this one dies out a bit slower. Okay, let us check the result. Okay, now you can see this. Yeah. Our system S+2, S+100. Then that's the value. S square plus 102 plus 200. And then what do I want to make here is C is equal to 1 divided by S to the power of 3 plus S square times plus 200S. Okay, I think it's this one. Okay, so that's the result. Yeah, you see one of them is minus in here, yeah. You know how to use INA plus, right? Yeah, go find out the answer. And so if I want to plot the result, how to plot the result? Yeah, make t first. T0, let's say it goes up to 50. Okay, what y is equal to this. Okay, so if I plot t comma y, what do I have? Yeah, so this is what I have. Oh, that's I only need up to 10, I think. Yeah, 10. Let's do it up to 10. I gotta plot again. Okay, now I see this. Let us plot together, yeah. This is the composite response, and then I will just plot this term. Let's say I plot this term. a legend, Ori. This is community. Okay, so you see, yeah, I haven't find out the correct representation yet. However, you see the speed of the response, yeah, it's not that much different. Okay, the speed of how it gets into the final value is not much of difference. Yeah, you compare it if I if I put let's say if I get the 100 compared to the 2, yeah, so I remove the 2 here, I remove the 2, why do I hate? Okay, you see, I cannot see it. It goes to 0 very fast. Yeah, so the one with the 100, it goes to 0 here. Can you see it? Come here. Can. When you come here, you will say, that's right. Okay. Yeah, the top one is still wrong. So how do we make it right? Okay, let us discuss that. Yeah. How do we get the correct representation of the dominant response? I have to remove this. So the system says it is how much? 1 over 200. Minus 2t becomes 1 over 196. And this is plus 9800. Correct, right? So what's the final value here? 1 over 200. Okay, so okay. So I will create another GS, G new FS, which is let's say M over S plus 2. Okay, I will put an M in here. I'll remove the S plus 100. Remove it. I will have only the S plus 2. Yeah. And now what is the final value if I have this one? Limit t go to infinity. Yeah, what? So S 1 over S times M over S plus 2, which is M over 2. And so this final value, it must be the same with 1 over 200. So what is M? What's M? 0.01. Yeah, so M should be 0.01. So that means this model here. Wait. Let me put another color. So that means this system it can be approximated by 0.01 over S plus 2. Okay, you get the idea? Yeah. So if it is this one, what is the result. Let us try to find it. um, C new 1 over what? Not 1 ya. 0.001 no lah, s square plus 2 times s ya. This one, right?
Oh, yeah.
That's the new C. Okay, this one, and then I Laplace C new, so that's what I get. So what I have to compare is this one with the new one, with the old one. Okay, so I will plot. Wait. Sorry ya. I have to define again the t. Let us define the t again to be exact. So this is still our old value, and the new one will be this one, yeah. Yep, and then we will plot them. No. Plot t comma y and t comma new. The legend, this is the original, and this is the approximated. Okay, so there you go. Yeah, they are almost the same, right? Original approximate the same. That's because we choose the dominant one. And if you want to do that, remember you have to compute the it's not working, the new constant in here, yeah. How do you compute the new constant? You use the final value theorem. Okay. Yes.
How close can we use the approximation
Uh,
between the dominant and the non-dominant one? So let's say it's s plus 2, right? But if it's not s plus 1, but s plus 2.1, can we still use the...
okay. That's too close.
Yeah, I mean like how close?
Yeah, I believe it will be if you have more than 100. If the multiplication is more than 100, let's say, then it's worth to be approximated in real case. I think even more than 10, you can see the difference. The bigger the difference is, the smaller discrepancies in the response that you will see. The bigger discrepancy is the poles. Yeah. Okay, just one more minute. I want to tell you how do we use this property. Yeah, how do we use this property? Yeah. This one? Oh, you have the recording already?
Wait.
No, it will not. So you see here, you have your GS. Can you limit your GS to second order system? Usually, but sometimes you cannot. Okay, it can be, let's say, fourth order system or fifth order system. It can be. Okay, and then your controller, can you limit your controller only to first order system? May not be, right? In reality, sometimes you need third order system or fourth order system controller. So combined together, the resultant controller could be greater than second order. Okay, so the closed loop system could be third order or fourth order. Now the way you design it is that when you have your closed loop poles, yeah, you place the two poles far away here, far away. Yeah, and then your desirable characteristic, you put it over here. You get what I mean? Yeah, with the correct controller, you can place the poles as you want, because the poles is going to direct or is going to affect how the system behaves. Yeah, you put the dominant one as your desirable characteristics. Okay, and then you put the other one further away from zero. Yes, that's correct.
So we can lower the order.
Technically, theoretically, yeah. Yeah. No, so,
Dominant pulse only one.
no. If it is second order, you have two, right? Second order system like this, it's two, right?
Yeah.
Is second order system the one that has damping? It's two. Maximum two lah. You still remember the time domain measures? Maximum overshoot, rise time, starting time. These are defined by the complex poles like this. You see?
So the question is, we have what we want to.
If your desirable characteristic is first order system, then your dominant pole is only one. If your desirable characteristic is like this, then your pole are two.
Dominant.
Two dominant pole, which is, let's say, -3 plus minus 5i. This is two, right? But they are complex poles.
Yeah.
And this is plus minus. Okay. So that is for today. We discussed about dominant pole already. Have a good time. Prepare for your exam. Yeah. See you again on Wednesday.